Welcome back. I'd like to start by saying a little bit more about a question someone asked in class, which is whether every matrix can be put in row echelon form. And the answer is yes. And let's look a little bit more closely how you do that. So you look at the first column of the matrix and you label the first entry A. And if A is non-zero, you're in good shape. What you do is you use A to kill all of the entries below it. Okay, and then A being non-zero, you can divide the first row by A to turn it into 1. So I'm actually going to be putting it in reduced row echelon form. Otherwise, I wouldn't need that step. Okay, if that's a misprint. If A is equal to 0, then you just pick a different row by permuting them to make it non-zero. And if you can't do that, that means the first column is all zeros and you're done. You don't have to touch it. Okay, so let's say we've dealt with the first column. So it's got a 1 up here and a bunch of zeros, or maybe it's all zeros, but never mind. And write the second column like this. The entry in the 2 place is B, and then everything else I don't care about. And now you just look at this rectangular matrix here with B in the upper left-hand corner. And well, you just repeat the same procedure with this matrix. So that is to say, if B is non-zero, you can turn it into a 1 and everything below it into a 0 and so on. And so you would, in that case, get to this situation. And now, if you're going into reduced row echelon form, there's one final step, which is to kill this guy right here by adding a multiple of the second row to the first. Another possibility is that all of these entries are 0, in which case, again, you're done. You don't have to do any more. So that's basically the algorithm. You just keep doing that over and over again, one column at a time. And at the end, you're in reduced row echelon form. Okay, so let's suppose that you've put a matrix in reduced row echelon form. And here I'll write a basic example, something like this. And the question is, what does that tell you about the solutions to an equation involving this matrix? So for example, suppose you'd gotten it down to this matrix. I've circled the three pivots. And I've labeled the two free variables, the two columns corresponding to a free variable. And what does that say? What's the significance of these two numbers, the 3 pivots and the 2 free variables? These are important numbers that you get out of this matrix. So the answer is, if you're trying to solve an equation AX is equal to 0, that is to say x is in the null space of A, what do we know about that? Well, the dimension of the null space is exactly the number of free variables. And what about the pivots? Well, I've talked about this. The dimension of the image of A is equal to the number of pivots. And final comment is that if you were solving a non-homogeneous equation, what does that look like? Well, there might be no solutions, or if there's at least one solution, then you get a whole translated plane of the dimension, the number of free variables. So let's do a simple example which illustrates this, and I recommend you park this example in your pocket, because when you're thinking about these things, it really makes it crystal clear what's going on. So take a matrix like this, really this very simple case. This is a map from R3 to R5, and it takes the vector ABC to the vector AB, 0, 0, 0. So it's transparent what it's doing. It's very easy to see these spaces. The null space, well, when does ABC go to 0? Well, that's exactly when A and B are both 0. So both A and B have to be 0, but C is arbitrary. So clearly the null space is one-dimensional, and it's the vector 0, 0, C. And that's this free variable. There's one free variable, so the null space is one-dimensional. On the other hand, what's the image of this map look like? The vectors that you hit by applying A and going from R3 to R5. Well, it's these vectors A, B, and the other terms are 0. So that's all AB, and that's clearly a two-dimensional space. And that corresponds to the two pivots. Now, this number of pivots is an extremely important number associated to a matrix, and we're going to give it a name. The rank of a matrix A is the number of pivots when you put it in row echelon form. Row echelon or reduced row echelon form, it doesn't matter. And just to be clear, I'm using the term pivots here in the sense of non-zero pivots. So, okay, well, that's all for now. There's some more to talk about today, which is the concept of bases and dimension, but I've split today's lecture into 2 videos. So that's the end of this video, and I suggest you go on to the next one.